Good evening. Okay, so we're going to show you the movie that I helped to produce in half an hour or so. But I thought that before I do that, I would explain the science of the movie. It's a science movie, and the movie is made so that you can enjoy it at a variety of different levels, even grade school students or retired people. But if you know the science background, you may be able to enjoy it a little bit more because you understand the concept behind it. So that's the purpose of my presentation here. So I'm the physicist, and there is something that I want to do with physics, which is to understand, discover the fundamental laws of nature, the law that explains everything. Of course, we don't understand these laws yet, but we are making progress in uncovering these fundamental laws and use what we have learned to solve some of the deepest mystery of the universe, such as the origin and the future of the universe. And this is a question that has been around for thousands of years. Since the ancient times, we humans have been interested in finding out how the universe began, how it works, and what's our place in it. And this question leads to a variety of religions and philosophy since the ancient times. But things changed 400 years ago. And part of that was Galileo Galilei pointed his telescope to a night sky and opened a new window to the universe. This made it possible to understand our universe not in terms of religion or philosophy, but in terms of science. And this initiated the scientific revolution, and this enabled us to address some of the mystery of the universe by scientific method. And for the last 400 years, we made remarkable progress in understanding the universe, and the movie presents some of our findings in sort of simple terms. And this progress is still continuing. So this is sort of a collage of a few newspaper and TV sections. And there are lots of new fundamental discoveries being made for the last few years too. And I have written 8 popular science books in Japanese to communicate some of recent excitement in this area. And they sold over 300,000 copies in Japan and have been translated into Chinese and Korean. There are 5 books in China, for example, and one of them got Science Prize. And so this leads to some interesting development. So this guy is Dimitris Kodopoulos. He is actually a Greek originally, but he got PhD in Osaka University in Japan, very fluent in Japanese, and he read my popular science books, and then got interested in making 3D movie. He was a curator of one of the 3 science museums in Tokyo, and I didn't know this, but if you're a curator in museum, you can actually write proposal to museum to try to do something new. So he asked me to help him write proposal to make science movie based on my book. But he was very ambitious. He wanted to have everything like quantum mechanics, standard model of particle physics, Big Bang, evolution of universe, and superstring in 30 minutes. And I thought this was crazy. But he was so enthusiastic, so I thought I should help him. And so somehow the proposal got through, and we assembled this team. So we are very fortunate to have to attract the service, retain the service of Mr. Shimizu. He's a horror movie director. You might have seen this movie called Ju-on. It's kind of a very scary movie. But he has an amazing visual imagination that you will see in some part of the movie. This is Mr. Yamamoto. He's a wonderful computer graphic technician. And then there are a few talented actors, including the man from 9 Dimensions, and this is your science guy. And then this became the 3D science movie, The Man from 9 Dimensions. This movie was originally made for dome theater, like in planetarium, and you are supposed to go there with the special glasses to see the 3D feature. Today, we're going to show you on this two-dimensional screen, but this will be also very nice. And in the year when it was released, it received the Best Educational Production Award from the International Planetarium Society, which is the highest award that this society gives to educational movie. It has been shown in Athens, Bangalore, Chicago, Denver. I realized that last year I also showed that in Munich, and it's missing here. This is from the show in Mumbai. So we had a Bollywood debut, and this is from Hamburg. So in the next 20 minutes or so, I will tell you about the science behind this movie. Now, I'm from Japan, and in the traditional storytelling in Japan, you are supposed to take off your jacket when things get into the main part of the talk. So that's what I don't go any further than this. But, okay, so this is going to be the main part. So we know that universe was born in 13.8 billion years ago. We know that in 3 decimal places. This is amazing that we know the age of universe with such accurate number. How do we know that the universe was born in 13.8 billion years ago? Well, there are a variety of evidence to support this. It started out with Albert Einstein. So Albert Einstein in 1915 completed his theory of gravity called the general relativity. It's a very difficult theory. And he applied it. He's very ambitious. And as soon as he completed the theory, he applied it to the entire universe and see what kind of solution it's going to give. And he found that the universe is expanding. And he thought that was crazy. It cannot be the case. And he abandoned the solution. That was a bad idea because 14 years ago, Edwin Hubble, who is an astronomer at Mount Wilson Observatory, discovered that the universe is expanding. So if Einstein had not abandoned this idea, he would have predicted it. But this is how it went. So by the way, this is a picture from Einstein visiting Mount Wilson. This is actually in the same city as my university is located. And in fact, we can see the Mount Wilson Observatory from the window of my office. So when I have a visitor, I brag that by saying that, well, we can see the observatory that detected the expansion of the universe. But unfortunately, this photo is apparently staged because, well, first of all, you cannot observe that the universe is expanding like this. Oh, universe is expanding. And also, more importantly, if you talk to professional astronomers, they will tell you that these are very precision instruments, and you are not supposed to smoke tobacco in this environment. So these are very suspicious. This is a photo of actually blackboard of lecture that Einstein gave in Oxford the same year. This one actually I took. University of Oxford is so proud of this, so they kept this blackboard. Now, another evidence, so I didn't say it toward the end. So if the universe was expanding now, this is what Hubble discovered. Universe is expanding now. So that means that if you go backward in time, universe should contract and become denser and denser. And therefore, there must have been a time when the universe was very dense and high temperature. So universe must have started with such a time. And from that, you can try to estimate the age of the universe. That's one way to try to estimate the age of the universe. There is another, essentially, actually, there are 3 classic reasons for us to believe that Big Bang existed. Another evidence is the following. So if the universe started with a very dense and high temperature soup, then you can actually calculate the ratio of hydrogen and helium in our universe by doing some quantum mechanical calculation, which is what George Gamow did right after the World War II. And he got the right answer. He got some ratio, assuming that the universe was started with a very hot and dense stage, the Big Bang. And then from that, he calculated a ratio of hydrogen and helium, and it precisely agreed with astronomical observations. So that's another evidence. there is a third evidence, which is the following. So suppose the universe started with a very hot and dense stage. Then at the beginning of the universe, right now we are all made of atoms, which are made of protons, neutrons, and electrons. These are charged particles. But when the universe was dense and hot, the protons and electrons are all sort of scattered around, and it became like an ion stage, so the light cannot propagate straightly. But after 400,000 years, the universe cooled down sufficiently, so they combined into neutral atoms, and the light started going straight. And this is something we can observe. And it was observed 1964 by Penzias and Wilson. And this is another evidence that the universe started with this kind of situation, where it started out with a very dense hot soup, but they eventually cooled down, became neutral atoms, and then light started being emitted. And we can see the light emitted from the beginning of the universe by right now observing light stretched to the microwave length. So if you are as old as I am, then you might have remembered that TVs are made of tubes. Right now, the TVs are very flat. But in those days, when the TV broadcast ended, you see some kind of noise on these tubes. About 10% of this noise are coming from the beginning of the universe, that you are observing the microwave coming out from the beginning of the universe. Unfortunately, these flat TVs that we have these days, you cannot see these things. But in ancient times, we were able to see that. Now, the universe, after that, universe cooled down. And because universe was made all of these neutral atoms, no new light has been emitted, and stars and galaxy was not still born. So about 100 million years, universe was in a very, very dark stage. And in fact, cosmologists call this as dark age of universe. But just like dark age in Europe had some kind of seed for Renaissance, the dark age of the universe had some kind of preparation for more modern times. That is that there are places where the atoms start gathering, and the structure started forming, and the clamps are formed, and they become stars and galaxies. And then about 100 million years after the Big Bang, the first stars are born. We now can observe some of these things by JWST space telescopes. And then billion years after, the galaxy starts forming. By the way, these are the pictures that you're going to see in the movie. And down here, you can see the clock, and it tells you how much time has passed since the Big Bang. And when we made this movie, we wanted to make sure that everything we tell you in the movie are scientifically accurate. So for example, these kind of images are also made based on the state-of-art structure formation simulation. And so we collaborated with a group at MIT and Harvard to get their help in simulating the formation of structure of galaxies and stars. And then about 9 billion years after the Big Bang, finally our sun and the Earth formed. And then life started forming on the Earth and evolved to us. So it took very long time for the sun and the Earth to emerge, and the life to begin, and develop to intelligent life like us, to ask questions such as how does the universe started, and how does the universe works. So this is kind of amazing. It's very important for universe. So I told you at the beginning that universe started out 13.5 billion years ago, but it also took the Earth to develop intelligent life 3.5 billions. And so it's a non-trivial fraction of the age of the universe. So it's very important for the universe to last very long in order to produce intelligent life. So that raises a question. Why is the universe the way it is, and how did it come to the existence? This is the main question of this movie. So let's go back to the Big Bang of the universe. So this is a sort of a caricature of the Big Bang that we use in the movie. I told you that 3 minutes after the birth of the universe, the hydrogen and helium nuclei appeared, and George Gamow calculated the ratio correctly. And but until after 0.001 second after the birth of the universe, protons and neutrons themselves are broken apart into even smaller objects called quarks. And only at 0.001 second after the birth, they combined into protons and neutrons. You can go back even earlier in the history of the universe, 0.00000000001 second after the birth. This is actually as much as we can tell scientifically based on the theory that has been experimentally tested. That universe until this time can be accurately described by what's called the standard model of particle physics. So in the movie, we're going to also introduce you the concept of the standard model of particles by introducing for you variety of elementary particles that appears in this standard model. For example, these are neutrinos. And there are 3 different kinds of neutrinos, and they mix with each other when they come down. And this is Mr. Kajita, who is my good friend. He is one of the persons who discovered that neutrinos mix with each other, and he's being honored by the Nobel Prize. And so in the movie, it shows that neutrinos are coming down from the sky and changing the flavor. And then photon, which is the quantum of this light, is another elementary particle that mediate electronic and magnetic forces. And then there is this Higgs boson that gives mass to all the elementary particles, and this was the Mr. Higgs was also another recipient of Nobel Prize. So this universe can be accurately described by this standard model of particle physics at 0.000000001 second after the birth until now. Before that, we cannot tell you for sure because we don't have any theory of elementary particle that have been experimentally tested. So beyond this is a speculation. But we can continue to ask questions. We can continue to ask the question, how was the universe like before that time? And there are theories that are proposed to explain it. So for example, there are reasons to believe that the standard model of particle physics is not complete. In fact, we know that in our universe, there are lots of other matters and energies that are not described by standard model. That the object that can be described by standard model is only small fraction of the entire universe. So one of the theories that goes beyond the standard model is called cosmic inflation. And if you believe those people who propose cosmic inflation, then it can explain how the universe was like until, I cannot even try to read these zeros. There are 36 zeros before one, after the birth. And there, the forces and the matter, even space and time of the universe were fluctuating according to the law of quantum mechanics. And in the movie, this was mirrored in the following way, that at the beginning of the movie, we'll see that the world of quantum mechanics, but then we'll see that at the beginning of the universe, there is something similar happening. And you might have heard the name Stephen Hawking, and he was one of the scientists who contributed also to the inflation model as well as many other aspects of gravity and cosmology. And he and his collaborator predicted that quantum fluctuation of forces and matter and space and time in our universe can be observed by the primordial light that we see in the microwave. This is Stephen Hawking when he visited Kyoto University when I was a first-year graduate student here. I'm the only one who is not wearing a tie, I think. So there are actually evidence that there was a quantum fluctuation of matter during the early universe, and this has been observed by precise measurement of this microwave coming out from the beginning of the universe. So you see that there is a bright spot and dark spots here. So these represent the fluctuation of microwave light, which is supposed to be explained according to Hawking's theory by the quantum fluctuation in the early universe. And these planted the seed for stars and galaxies of the universe. I told you earlier that in the dark age of the universe, there was no light, there was no structure, there were no stars. And suddenly, towards the end of dark ages, about 100 million years after the birth of the universe, the structure started forming and the first star emerged. And the reason for that was that there was a tiny clump in the universe. And that actually evidently came from these primordial quantum fluctuation. And so in some sense, we can say that our stars and galaxies are formed by quantum fluctuation at the beginning of the universe. And in the next 10 years, there are lots of experiments and observations which try to directly detect these effects. And this Japanese satellite, Lightbird, is one of the attempts which is being planned to be launched toward the end of this decade at the institute that I was director of until last year. And in fact, the detection of gravitational wave, which happened 80 years ago, opened a new window to the universe. And it may also solve a variety of mysteries of our universe. It's already led to Nobel Prize to these people for the direct detection of gravitational waves. But to understand the early universe, we need more fundamental theory that goes beyond the standard model of particle physics, that unifies the microscopic world of quantum mechanics and the macroscopic world of gravity. And the only consistent way we know how to do this is superstring theory. So in this movie, we'll also introduce you the concept of superstring. Superstring theory postulates that fundamental building blocks are not a point particle, but strings. And string theory is defined in 9+1 dimension rather than 3+1 dimension that we live in. We think we live in 3 dimensions because there is the 3 different directions that we can go. But in string theory, it tells you that you actually live in 9 dimensions. So that's where the name, the man from the 9 dimension, comes from. So, but that means that, since we live in 3 dimensions and the theory tells you it's in 9 dimensions, so there are 6 extra dimensions. And this 6 extra dimension is supposed to be in a small space, and it's called Calabi-Yau. And it's not visible to us directly, but the structure of elementary particles are supposed to be encoded in the geometry of this Calabi-Yau manifold. So one of the things I'm doing as a scientist is actually try to derive quantitative prediction of physics in our world, 3+1 dimension, from the geometry of Calabi-Yau manifold. But Calabi-Yau manifold is actually mathematically very complicated object, and we have very limited tool. And so we need to develop mathematics to understand it. And so in the movie, toward the end, we'll see the power of mathematics also in the movie. So anyway, so the man from 9 dimension is a metaphor of theory of everything. So when Dimitris Kodopoulos came to see me, tell me that he wants to have this movie which has quantum mechanics, standard model, Big Bang, structure formation, string theory, everything. Well, I was trying to figure out how you can put everything in 30 minutes. And after doing various brainstorming, we came up with the idea that we can have this man from the 9 dimension, which is sort of metaphor of theory of everything. And he takes us to the macroscopic world of elementary particles, and going back the history of the universe to the beginning of the universe and Big Bang and superstring. And so that was a device for us to help us put all these concepts into 30 minutes. And you also see that as you see the movie, in the first half of the movie, you go to the small world, the world of elementary particle and quantum mechanics. But then there is a small break, and then gravity is introduced, and then you go back towards the end of the history. So that is how the movie is structured. But these are all the science part of the movie. The movie is also fun to watch. When I was asked to help supervise the movie, I went to the museum to see what kind of people are coming to the movie. And I see like elementary school children, I see some young couple, and some retired people, some working people. So I wanted to make movies that can be enjoyed and appreciated by people in a variety of background. And so you can enjoy the movie as it is, but I hope with this introduction, you can understand the science of the movie also a little bit better. So I imagine you might have some question about the movie. I'd be happy to try to answer. I cannot promise always be able to answer, but I try.
Hi, I have a first question. Why is it 9 dimensions?
Very good question. So in fact, the professor in the movie, on the blackboard, he was trying to explain why it's 9, basically. And the reason is roughly as follows. So in this theory of superstring theory, all the fundamental objects are supposed to be made of strings. And strings fluctuate and vibrate, and it makes some quantum mechanical fluctuations. And the requirement that the strings quantum fluctuate, but at the same time, there are photons, there are light, and the light we know propagate, light are fastest object in the universe, that there is nothing faster than the speed of light. And this is related to the fact that photons, which are the quanta of light, are massless. It doesn't have mass. And if the string vibrates, it increases the mass. And if you have vibrate in more dimension, you have more masses. So combination of the fact that the strings vibrate, and when it vibrates, it increases the mass, and the requirement that the light propagates at the speed of light, determine the consistent dimension to be 9. And this is actually rather interesting because in any other theory of physics, like Newton's mechanics or Maxwell's theory of electromagnetism or fluid dynamics, all these theories can be defined in any dimensions. String theory, as far as I know, is the only theory which says that it has to be in this dimension. Okay? It didn't come out exactly in 3 dimensions we live in, but I think it's a blessing in disguise, because that means that we have extra 6 dimensions to play with, and it gives you interesting structure to our universe. So it's interesting. So it's interesting because eventually, if we want to explain everything from fundamental laws of nature, we also want to explain why we live in 3 dimensions. And, but if you start with Newton's theory or Maxwell's theory of electromagnetism or Newton's theory of mechanics, since it can be defined in any dimension, there is no hope that you can explain why we live in 3 dimensions. But since string theory tells you that it has to be 9 dimensions, there is a place to start. So there, if we work very hard, we may be able to explain 3 dimensions. So that's sort of one of the interesting things about string theory. Thank you for your question.
First of all, thank you for your presentation. And before I start, can you lower the volume? It's like
okay, I cannot
unpleasant.
do that, but somebody down there can do that.
Thank
or
you.
maybe I can try to speak slowly.
You're not the problem. So what's the difference between string theory and superstring theory?
Okay,
I
very
still
good.
don't quite
Yeah.
get that.
So sometimes
Thank
we
you.
say string theory, sometimes we say superstring theory. So super refers to, we say superstring theory because we wanted to sort of inflate the value or something like that. But it has to do with some particular symmetry that theory has. So you have actually, originally, the string theory was defined to try to explain property of protons and neutrons and those elementary particles. And this theory did not have this symmetry called supersymmetry. But later, people realized the theory becomes much nicer. And you can remove various undesirable features of original proposable string theory if you postulate that string theory also has supersymmetry. So superstring is sort of called super because it's a string theory with supersymmetry. So it's called supersymmetric string theory, if you like. And that's a distinction. So, but sometimes, often, since when we study superstring, when we say string theory, when we study string theory, we often just study superstring theory. So sometimes we mix these two terminologies together. But there is this distinction. Yes, thank you for asking.
We have a third question here.
Yeah, I'm sorry. At the very beginning, you said that all started from a kind of soap. A question: what made soap exist, happen?
So you're asking whether the soul exists or not?
Everything started from soap. Where that soap happened from?
Sorry, soap?
Soap, yes. You said that in your film, that the Big Bang Theory, at the very beginning, soap existed. And from that soap, sort of soap.
Sorry, I'm confused by the question. Maybe you can interpret.
I think she means soup.
Soup. Oh,
I'm sorry.
soup. Yes.
I'm sorry, soup. Sorry for my accent.
Yes. So I was asking more spiritual. I thought you were asking more spiritual questions. Okay. So what I meant by soup or cosmic soup is the beginning, the stage of the beginning of the universe, where universe was very dense and hot, and temperature was very high. And the reason we believe that was the case is because the universe is now expanding. So if you go backward in time, universe must have been a time when universe was very hot and dense. And there are a couple of more evidences for this I explained in my lecture. One is this calculation of ratio of hydrogen and helium, which came out right. And then there is also cosmic light coming from the beginning of the universe. All these evidence suggests that there was a very hot, dense beginning of the universe. So that's an evidence, yes.
Hello, thank you
Yes.
very much for the lecture. So, coming back to that very, very dense and hot state, can we measure that energy? And then the subsequent question is, if we can measure that energy and we know the rate that the universe is expanding, could we predict how much it can expand before it stops?
Yeah. So, indeed, that's a very good question. So, basically, once we know the initial temperature of the universe and density, we can just use Einstein's equation to see how the universe evolved since then. And this is exactly how cosmologists study the universe. You combine this initial data with the cosmic expansion and compare that with what we observe now. And then from that, try to infer the more detail about the initial conditions of the universe. And if we know everything about the composition of the universe, this is all we need to know. One missing thing is that we don't know everything about what the universe is made of. In my lecture, let me show you the diagram. I showed you it's a little bit later, so please bear with me. Oh yeah, here. So by studying the property of the universe, we discovered that actually the most of the universe is made of something we don't really understand. That we only understand 4% of the universe. And in fact, this 74% is called dark energy, and this is one of the most mysterious parts of the universe. Because until now, we thought we understand the expansion of the universe. Until now, I mean that until about 25 years ago, we thought we understand the expansion of the universe. That we refine the measurement of Hubble, and we measure how the galaxy goes out in the universe and how the universe expands and what the history it is, and compare that with the prediction of Einstein prediction, and it was consistent. And then, 25 years ago or so, by measuring the expansion of the universe more precisely, people discovered that right now, the universe started to accelerate its expansion. So until now, what happened was that there was a big bang, and then there was a huge expansion of the universe, and it started to actually, the expansion rate started to decrease. The reason is that there are lots of matters in the universe, and there is a gravitational attraction, and they try to prove them together. So therefore, the expansion speed gradually started to decrease. But more precise measurement shows that in recent times, actually, the expansion rate started accelerating, and the speed is now increasing. And this is very mysterious because this doesn't happen in ordinary matter, because gravity is supposed to attract each other, not expand. And the only way to expand it is that there is actually a mysterious energy in the universe, which is not ordinary matter, like atoms or anything like that. And so since we don't understand what it is, it's called dark energy. And there are candidates of the theory to explain it, but until we exactly understand the nature of dark energy, we cannot predict how the universe is going to be like from now on, because it depends on the behavior of dark energy. And this is actually something we are going to measure precisely in the next 10 years or so.
I'm afraid we're running out of time. We can take one more question on the mic, but after that, Professor Hiroshi will be available by the bar. He'll be exchanging questions for cocktails. Feel free to ask and argue as much as you can. For now, who are we doing?
Yes.
Yes.
Thank you so much for the lecture. I would like to ask you if you can see any relationship between the expanding of the universe and the expanding of the human conscience.
Expansion of human conscious. What is the expansion of human conscious?
It's like we're getting more conscious about everything that is around us, more conscious about our senses, more conscious about there's more something more than atoms inside the atoms.
Is the amount of conscious expanding in time?
It's like in knowledge, I think. In matter of knowledge.
Okay, so knowledge, so you say that expansion of knowledge and expansion of universe, are they related? Well, that's a very profound question. So there is actually a mathematical way to measure the amount of knowledge called entropy. And indeed, there are certain relationships between expansion of universe and the property of entropy of the universe. And there is some relation in that sense. I'm not sure whether this is the knowledge of human per se, because human is, in my view, of course, people in different religious ideas may have different concepts about the role of human in this universe. But I myself is a very Copernican in seeing that humans are just living on this tiny planet in this entire universe. So the role of human is very small. So in that narrow sense, there is no obvious direct connection between human consciousness and the expansion of the universe. But if you think it in a more broader term, like amount of information in the universe versus size of the universe, yes, there are certainly relations between them.
Please give it up one more time for Professor Hiroshi. Thank you so much for the nice talk, and thank you so much for coming to Science and Cocktails.